And so we've discussed what happens to the Laplace transform of the derivative of a function. Now we want to discuss what happens to the Laplace transform of an integral. And it's a very interesting relationship that will get similar to the derivative relationship. Laplace transform of the integral of a function, definite integral from 0 to t, and we'll use the integration variable u of f of u du, is going to be equal to 1 over s times the Laplace transform of f of t. This is a function of s, and this is also a function of s. And I want to make a point to point out here that the lower bound of integration here in this definite integral is 0. This is going to be important to us when we go through and prove the formula. If you change the lower bound, the formula is going to be a little bit more complicated. Let's go through and prove this. First, we'll introduce the function f of t to be defined as definite integral from 0 to t of f of u du, in which case capital F 0, the limit of this as we put 0 on the right, is going to be equal to 0. You get the integral from 0 to 0, which is going to be 0. And likewise, note that by the fundamental theorem of calculus, the derivative of f of t, or f prime of t, is equal to lowercase f of t. And the proof of this is really simple. It uses the formula for the first derivative, this formula right here. Only we apply it to capital F prime. So we know that capital F prime is the same as lowercase f of t. So this equation holds. And using the Laplace transform formula for the first derivative, the Laplace transform of f prime is going to be s times the Laplace transform of f minus the limit as x goes to 0 from the right-hand side of capital F. We know that by the definition of f, this is 0. And so the Laplace transform of lowercase f of t is equal to S times the Laplace transform of capital F of t. Which completes the proof. This is saying that S times the Laplace transform of the integral from 0 to t of a function of lowercase f this times s is equal to Laplace transform of f, and dividing by s gives you this equation right here. And we can even generalize this, and I'm not going to go through and prove this, but this equation actually generalizes to Laplace transform of the integral from a to t of a function f is equal to 1 over s times the Laplace transform of f minus the integral from a to s of f. And it'd be a good thing for you to go through and check this using the method that we use here. It's a very similar check. Another very interesting property that the Laplace transform satisfies is if f is a piecewise continuous function, and of exponential order, and lastly, if the Laplace transform of f is equal to capital F of s, just to help make the notation a little bit cleaner, then the Laplace transform of t times f of t is going to be equal to negative the derivative of the Laplace transform of f, or of lowercase f. And this is valid for s greater than a. Proof of this uses the definition of the Laplace transform, like all of these proofs. We go through and take the derivative, as long as f satisfies the conditions of piecewise continuous. And we can go through and write that this is going to be the same thing as the derivative of this function, the integral of the derivative, will be negative s times e to the negative st f of t dt. Sorry, negative t here, because this is the s derivative. Which is the same thing as negative integral from 0 to infinity of e to the negative st times t f of t, which is negative the Laplace transform of t times f of t. Not only that, but if you apply this multiple different times, we get the corollary that the Laplace transform of t to the n times f of t is going to be negative 1 to the n times the nth derivative of the Laplace transform of f. Which is valid for s greater than a. So all of these properties are super useful when applying the Laplace transform to linear ordinary differential equations and linear partial differential equations, which is why we're kind of going over these properties. The next property is how the Laplace transform acts on periodic functions. So functions like the type we considered for the Fourier series. So in the following, we'll say that let a function f of t be periodic with period p. Then f of t is equal to f of t plus p, and so on and so forth, all the way up to f of t plus n times p for any integer n. Then the Laplace transform of the function f is equal to 1 over 1 minus e to the negative p times s times the integral over 1 period of e to the negative st times f of t dt. And the proof of this is relatively straightforward to go through. We know that the Laplace transform of function f is integral, improper integral from 0 to infinity of e to the negative st times f of t dt, which, because f is periodic, is going to be the sum from n equals 1 to infinity over every period. So the integral from n minus 1 times p to np of e to the negative st f of t dt. And if we consider what the integral is on any one of these periods, note that we can make the u substitution of t is equal to u plus n minus 1 times p. And for this u substitution, dt is going to be equal to du. This integral will be the same as the integral from 0 to p of e to the negative s times u plus n minus 1p times f of u plus n minus 1 times p du. And because of the periodicity of the function f having period of p, this then will be equal to e to the negative s times n minus 1 times p times the integral from 0 to p of e to the minus su times f of u du. And so the summation that we have here for the Laplace transform then is equal to the infinite summation from terms of this form, where this doesn't depend on n at all, and this can actually be rewritten specifically. This is going to be the integral from 0 to p, which doesn't depend on n, so it comes out of this infinite sum, times the sum from k equals 0. We re-index k to infinity, e to the negative sp times k, negative sp to the power k. Which is an infinite geometric series with a equals 1 and r equals e to the negative sp, which is less than 1. So we know that this is going to converge to 1 over 1 minus r. The Laplace transform of f of t then will be equal to the integral of the function over the first period times e to the negative s times u multiplied by 1 over 1 minus e to the negative s times b. Which gives us the equation that we wrote down originally. So this is also a very, very useful formula to apply in many applications. Specifically when we're talking about the Laplace transform of periodic signals. Relies on the formula for the sum of an infinite geometric series, and it also relies on u substitution when we go through and evaluate our integral and capitalize on the periodicity of the function f. So for a quick example, we'll just consider the sawtooth function. F of t with period p of 1. We know that this looks like this. As a repeating pattern. All the way to infinity. So applying this formula then gives us that the Laplace transform of this function is going to be equal to 1 over 1 minus e to the negative s times the integral from 0 to 1 of t times e to the negative st. Which simplifies to 1 over 1 minus e to the negative s times negative e to the negative s over s minus e to the negative s over s squared plus 1 over s squared. So this is very neat, and all of these properties can be summarized in another little table here that I'll write down. Just for your convenience and application problems. So if we have the original function f of t, then the Laplace transform is denoted by f of s. This is the integral from 0 to infinity of e to the negative st f of t dt. If we take the Laplace transform of f prime, we've shown that is the same thing as s times the Laplace transform of f minus the limit as we approach 0 from the right of the function f. F double prime of t is equal to s squared times the Laplace transform of f minus s times the limit of f as t goes to 0 minus the derivative of f as t goes to 0 on the right. And we've shown that the integral from 0 to t Laplace transform of a definite integral is going to be 1 over s times the Laplace transform of the original function f. And lastly, the Laplace transform of e to the at times the function f is going to be the Laplace transform of s minus a. This is what we call the first shifting theorem. So if we have a first shifting theorem, we're going to have a second shifting theorem. And this is important for piecewise defined functions. And what we'll first do is define what's called the unit step function. Also sometimes known as the Heaviside step function. And typically we note this as u a of t is going to be equal to the piecewise function that's 0 when t is less than or equal to a, and 1 when t is greater than or equal to a. Or sorry, yeah, strictly less than a. It's 0 when t is strictly less than a. And the Heaviside step function is just this function when a is 0. So this is a function that is 0 up to a, and then at a it jumps up to 1. As a function of t. So the Heaviside subfunction is when a is 0, and what's interesting here is that you can always write a shifted function, the unit step function ua of t is going to be the Heaviside step function evaluated at t minus a. So it's the Heaviside step function, or the unit step function, that jumps at 0 but shifted by a. And what's also interesting is that any piecewise defined function can be written involving these jump functions. Say if you take the function f of t, defined as t squared for t from 0 to 1, and sine of t for t greater than 1. Then f of t can be written as t squared times u0 of t minus u1 of t, because u0 and u1 are 0 for t less than 0. This is equal to 1 for t greater than 0 but less than or greater than 0. And this is still equal to 0, so this entire thing is 1 when t is between 0 and 1. And then it reverts back to 0 again when t is greater than or equal to 1. And plus sine of t times u1 of t. So this piecewise function can be written like this in terms of this unit step function. This is very, very important in applications. It's so important, in fact, that we have a theorem called the second shifting theorem that tells us what happens when we take the Laplace transform of a function times a unit step function. The Laplace transform of the step function ua of t, some function f that's shifted by a, is going to be equal to e to the negative as multiplied by the Laplace transform of the original function f. This is valid whenever a is greater than 0. And the idea now is that we want to go through and prove this, but the usefulness of this theorem comes in that it allows us to take the Laplace transform of any piecewise defined function that's nice enough, which is very, very useful for solving both linear partial differential equations and ordinary differential equations when we have a forcing function that's discontinuous. And this happens quite often. So to prove this, we're going to start from the right-hand side. We'll look at e to the negative as times the Laplace transform of f is the same thing as e to the negative as times the integral from 0 to infinity of e to the negative st times f of t dt, which, if convergent, with the same thing as the integral from 0 to infinity of e to the negative s times t plus a times f of t and if we introduce a new variable, t is equal to, or u, so u is equal to t plus a, and du will be equal to dt, and this integral will be the same thing as the integral from a to infinity e to the negative s times u f of u minus a du, which is the same thing as the integral from 0 to infinity of the step function ua of u times f of u minus a times e to the negative s times u du, which is the exact definition of the Laplace transform of the function ua of t times f of t minus a. Which completes the proof. So the first and second shifting theorems have the operation of shifting a common feature. The difference is that in the first theorem, this operation is applied to the function of s, while in the second, it is applied to the function of t. But the idea here is that these are both very, very useful theorems for calculating a given Laplace transform. And the last theorem that we want to go over involving calculating Laplace transforms is called the Convolution Theorem. And this is yet another theorem that's going to give us a very powerful method for computing Laplace transforms. So before we can do this, we have to first define the convolution product of two functions. So let f of t and g of t be two piecewise continuous functions the convolution product of the two functions f and g is defined as the following integral. Or we denote typically convolution with a star. So new function of t, and specifically it's the integral from 0 to t of f of t minus w g of w dw. And almost immediately, one of the things that we can prove, would be a good exercise to prove, is that the convolution product is commutative. So the convolution product of f of g is the same thing as the convolution product of g with f. And this is a relatively easy thing to prove. So we'll do that right here. We have that f convolved with g, and we sometimes say f convolved with g or g convolved with the f, is the integral from 0 to t of function f of t minus w times g of w, and it's the integral with respect to w. If we introduce the new variable t minus w is equal to u, then dw is equal to negative du, and so under this transformation, this u substitution, this integral is the same thing as the integral from t to 0 of f of u times g of w, which is t minus u. And dw is negative du. And so this negative sign flips the bounds of integration, making this the integral from 0 to t of g of t minus u times f of u du, which is the definition of convolution of g with f, or g convolved with f. And let's do the following example to really understand what exactly the convolution product is doing. We'll look at f of t is equal to the constant function t from 0 to 1 and 0 otherwise, and take the function g of t to just be the function 1 on the interval from 0 to 1 and 0 otherwise. And the convolution product of f of g is the integral from 0 to t of f of t minus w, or g of t minus w. This is the same thing as the convolution product of g with f times f of t, f of w dw. And this is where the real power of the Heaviside step function comes into play, because f of t can be described as t times the Heaviside step function of t minus the Heaviside step function of t minus 1 and g of t is just the Heaviside step function minus the Heaviside step function shifted by 1. And so the integral from 0 to t of g of t minus w times f of w is just the Heaviside step function of t minus w minus the Heaviside step function of t minus w minus 1 times f of w, which is w, times the Heaviside step function of w minus the Heaviside step function of w minus 1. dw. And if we go through and break this into multiple separate integrals, we get this is the integral from 0 to t of the Heaviside step function of t minus w times the Heaviside step function of w plus the Heaviside step function of t minus w minus 1 times the Heaviside step function of w minus 1 minus the Heaviside step function of t minus w times the Heaviside step function of w minus 1 minus the Heaviside step function of t minus w minus 1 times the Heaviside step function of w, all times w dw. And we can break this into parts to see exactly what this is going to converge to. And so I'm going to leave the rest of this example as an exercise for you to figure out. But I do want to show what this is giving as a function of t. And this is a very, very helpful graphic that will help you visualize and kind of think of what the convolution is doing. So here I've defined both these two functions. F of t is t from 0 to 1 and 0 elsewhere. And g of t is just the step function, or the Heaviside step function of t minus the Heaviside step function of t minus 1. It's the unit step function on the interval from 0 to 1. And if we go through and visualize what this convolution is doing, as we can think of it as sliding the function g through the function f and calculating the integral of the product. Which results in this black function right here. You see the domain of the dependence of the black function is larger than the domain of dependence of the two individual functions that we started with. Furthermore, the function f is actually smoother than both of the two original functions that we started with. So the convolution is in some sense a smoothing operation, which is very cool. And this is an extremely, extremely useful operation in many applications, specifically in signals processing. But for us, in terms of Laplace transforms, we're going to have a very strong theorem called the Convolution Theorem, which is going to allow us to use the convolution directly in terms of going through and calculating the Laplace transform. And the theorem that we're going to show is called the Convolution Theorem. And it's surprisingly straightforward. Two functions whose Laplace transforms exist. The Laplace transform of the convolution of those two functions is equal to the algebraic product of the Laplace transform of f times the Laplace transform of g. And the proof of this theorem relies on the definition of both the convolution and the Laplace transform. You know that the Laplace transform of the convolution of two functions is going to be the integral from 0 to infinity of e to the negative st times the integral from 0 to t of f of t minus u g of u du. And this is the same thing as the integral from 0 to infinity of e to the negative st. And let me actually use w as my integration variable here. This will be important in a second. times the integral from 0 to infinity. This integral is the same thing as the integral from 0 to infinity of the step function, the unit step function u, evaluated at w of t times f of t minus w g of w dw. Which is the same thing as the integral from 0 to infinity, integral from 0 to infinity. We switch the bounds, we bring g of w to the outside, dt dw. So we notice that we have a rectangular integral here, and by Fubini's theorem, in multivariable calculus, we can write this integral in either order. So this becomes the integral from 0 to infinity of g of w times the integral from 0 to infinity of e to the negative st unit step function of w, or shifted by w at t, times f of t minus w dw dt dw. And by the second shifting theorem, this entire thing itself is the Laplace transform of u(w) of t times f of t minus w is just going to be none other than the Laplace transform of f multiplied by e to the negative s times w. This is the same thing as the integral from 0 to infinity of g of w times the Laplace transform of s times e to the negative s times w dw, which is equal to f of s times the integral from 0 to infinity of e to the negative sw dw times g of w which is just the Laplace transform of g. And this is proven. So I recommend going through and testing this, using some of the previous results of the table to check this for a number of different examples to be some good practice. But this is a very powerful theorem and is used, as well as all the other theorems are very powerful, but this is probably one of the most powerful theorems that we have for evaluating Laplace transforms, and the applications are numerous. But thank you very much for tuning into the lecture. I hope you had a great day and learned something.